main purpose to explain the distortion and residual stress in quenched steel cylinders using the simulated strain-based approach. Due to time constraint, the presentation will be limited to a comparison of the two approaches for such an explanation using application of cylindrical specimens. The first approach was invented in the 1930s when measuring the residual stress distribution in the cylinder became possible. The approach used the concept of thermal and transformation stresses. This approach was revived in the 1960s. Here, the author will refer to it as the estimated stress-based approach. The second approach, which uses the results of heat treatment simulation, appeared in the early 2000s. It is now called the simulated strains-based approach. For simplicity, the explanation uses mainly for quenching results of the iron-nickel alloy cylinders. This slide shows a brief chronology of the studies on residual stress in quenched steel cylinders, which are discussed in this presentation. First, these residual stress were measured and estimated by Buller et al. Based on the concept of thermal and transformation stresses, and reported in 1932. This includes a study using iron-nickel alloy cylinders. In 1966, Rose attempted to explain the mechanism of residual stress generation based on the same above concept and his research on phase transformation. Lammerstofer et al. Applied the finite element analysis to residual stresses of quenched iron-nickel alloy cylinders. In this work, quenching experiment and residual stress measurement were also performed and were reported in 1985. In 2007, Arimoto and Funatari used the simulated strain-based approach to explain the quenched residual stress generation in iron-nickel alloy cylinders. First, we will consider the case in which phase transformation doesn't occur. This slide shows distribution changes of axial stress in a pure iron cylinder during quenching, which was estimated by Backholtz and Buller. The shape of the residual stress distribution is based on the measured value. The residual stress in 50 mm diameter pure iron cylinder quenched in water were determined by the Sachs method. Based on these results and qualitative discussion, stress distribution were estimated in 3 stages. Rose explained the residual stress generation in quenched pure iron cylinders. Temperature difference between the core and the surface is maximum at time W. This difference causes tensile stress on the surface and compressive stress in the core. Since the plastic phenomena on the surface correspond to the hatched stress, the discussion will be made using curve B. Core stress is balanced with the surface stress, which changes roughly according to curve C. The problem is that it doesn't explain why hatching stress is caused in plastic phenomena. Rose applied his approach for explaining the mechanism of residual stress generation in water-quenched carbon steels. During water quenching of a tool steel cylinder, only the near surface hardened. This is evident from the time temperature transformation diagram of continuous cooling. In this two-stir cylinder, paralytic transformation occurs at the core, followed by martensitic transformation near the surface. The lower part of here shows the estimated stress changes on the surface and core of the cylinder and the distribution of residual stress measured. A similar diagram for a stir cylinder quenched by water is shown on the right side. In this case, the entire piece transformed to martensite during quenching. The measured residual stress distribution is the opposite of the case of the left side. An attempt to explain the generation of residual stress by the combined effects of thermal and transformation stresses was initiated by Buller and Shire. To illustrate these effects, iron nickel alloy, which has a simpler phase transformation behavior than carbon steel, was chosen as the cylinder material. They quenched cylinders of 50 mm diameter with different nickel content in water at 0 degrees Celsius and measured their residual stress distribution. The figure shows only the axial component extracted from the original figure. The relationship between start and end temperature of martensitic transformation in iron nickel alloy and nickel contents is investigated and shown in the right figure. Note that diffusion type transformation does not occur in iron nickel alloys. Buller and Shire estimated qualitatively changes in specific volume and stress during the quenching process of iron nickel alloy cylinders and drew a schematic diagram. In the figure, position 1, 2, and 3 are provided in the cylinder. Specific volume change is assumed to be caused by thermal contraction and transformation expansion, and their changes at position 1, 2, and 3 are graphed. Distribution A was estimated at time Z1 when martensitic transformation begins at position 1. At Z2, distribution B occurs when the transformation ends. The distribution C was estimated to occur at the midpoint between Z3 and Z4. At Z6, distribution D is generated, and stress distribution E is generated when the whole material cools down. This figure depicts the generalized relationship of stress strain and distortion in quenched parts. First, the volume changes due to temperature and concentration are expressed at the thermal and diffusion strains, respectively. In the case of phase transformation, the resulting volume change is represented as transformation strain, and the related plastic behavior is described as transformation plastic strain, while produced elastic strain relate to stress directly. The deviatoric component of stress contribute to generate plastic, transformation plastic, and creep strains. The sum of the various strain in the total strain, which relate to the distortion of the parts. This figure is useful for explaining the cause of the distortion and residual stress. This slide shows the cylinder specimen is modeled at a cylinder of infinite length. That is, a disc cut from the auxiliary center portion of the cylinder is modeled with one layer of asymmetric elements. The lower part of the model is actually constrained, while the upper part remains flat and can be freely displaced in the actual direction. This model was used in the simulation of Lammerstofer et al. And by Arimoto and Funatan. Here is the property data of the ionic alloy measured by Lammerstofer et al. For their simulation. The graph on the left side shows the temperature curves of specific heat and thermal conductivity. The right-hand graph depicts temperature-dependent data for Young's modulus, Poisson ratio, and hardening modulus. These data were also used in the simulation by Arimoto and Funatan. Since the work by Lammerstofer et al. Is in the early stage of simulation, no rigorous model was used for the multi-synthetic transformation. That is, the effect of transformation expansion was handled by modifying the thermal expansion coefficient as shown in the graph. While Arimoto and Funatan used Koizumi-Marburger's equation for the kinetics of multi-synthetic transformation. For transformation plasticity, Lammerstofer et al. Treated the effect as temperature dependence of yield stress as shown in the graph. Arimoto and Funatan is used a general model which takes into account the transformation rate and deviatoric stress with an experimental factor. This slide shows that the simulated temperature change at the core of the ionic alloy cylinders is in good agreement with experiment. Note that surface measurements were used as boundary condition for the model. Simulated actual residual stress is in rough agreement with measurements by Lammerstofer et al. And Buller and Shire. Various types of strain can be obtained from the simulation. First, the thermal strain plus the transformation strain is called expansion strain. Changes in the expansion strain are shown graphically here. Changes in the distribution of actual elastic, plastic, transformation plastic, and total strains can also be plotted as shown here. Please note the total strain is derived from the additive equation. Since the absolute amount of elastic strain is smaller than other strain, the graph is enlarged. Here it is verified that the shape of the distribution elastic strain in the final cooling state is obtained from the expansion plastic, transformation plastic, and total strain. Here is the equation for determining the elastic strain. That is, first the plastic strain C and transformation plastic strain D are added. Then the sign of the added amount C plus D is reversed. Minus C minus D is included in the equation. Then, by subtracting the expansion strain A from the total strain E, the distribution E minus A is obtained. Finally, the elastic strain is derived by adding the distribution minus C minus D and the distribution E minus A. Here, simulated actual elastic strain are illustrated again. For comparison, simulated actual stress are shown on the right side of the slide. The curve shapes in both graphs are in good agreement. Thus, if we know the mechanism of elastic strain generation, we understand that of stress. The following slide will illustrate the reason for the generation of elastic strain from the various strain changes. At 30 seconds, the time when quenching begins, strains are shown by the thick red lines. Here, for convenience, the figures of the enlarged elastic strain is moved to the right side of the original figure. At 0 second, the expansion strain distribution is horizontal and 0. This is because the heating process is not taken into account in the simulation. The horizontal distribution of elastic, plastic, and transformation plastic strain indicated that these are all not occurring. The total strain is also in the 0 horizontal. Water quenching causes a rapid decrease in the surface temperature of the cylinder. The distribution of expansion strain at 2 seconds is reduced on the surface side due to thermal contraction. The very surface side undergoes a martensitic transformation, so the reduction in expansion strain is reversed. Plastic strain is positively distributed at the surface, opposite to the expansion strain. It is negative inside. The transformation plastic strain decrease in the range where martensite occurs. The elastic strain is affected by the above described strain changes. It is negative in the martensitic zone with a sharp positive peak inside the martensitic zone and the negative distribution further inside. The total strain in the horizontal distribution is reduced. The slide shows the various strains at 6 seconds. Compared with 2 seconds, cooling progressed from the surface and martensitic zone extended to the interior. Thus, the range of expansion plastic and transformation plastic strain are extended inward. For elastic strain, the compression zone on the surface side also expand inward, and the tensile peak moves to the inside. The total strain in the horizontal distribution decreases further. The slide shows the distribution of various strains at 10 seconds. As in the previous slide, the martensitic zone expands as cooling progresses from the surface. A similar trend can be seen in the expansion plastic, transformation plastic, and elastic strain. The plastic strain is lowest at the cylinder core. The elastic strain is lowest at the surface. The total strain in the horizontal distribution decreases further. The slide shows the various strains at 14.7 seconds. The same cooling and phase transformation phenomena as in the previous slide continue to occur. Thus, a similar trend can be seen in the expansion plastic, transformation plastic, elastic, and total strains. These are strains at 19.8 seconds. The same trend of changes in the strain distribution can be seen as in the previous slide. The expansion strain at the cylinder core is now less than minus 0.005. The slide shows the various strains at 25.9 seconds. The distribution changes show the same trend as in the previous slide. The total strain has decreased considerably. The slide shows the various strains at 36.4 seconds. The distribution changes show the same trend as in the previous slide. while the total strain has begun to increase. The expansion strain at the core is at its lowest value, while the elastic strain at the core is at its highest value. This increase corresponds to a decrease in expansion strain. The slide shows the various strains at 44.9 seconds. The strain distribution shows the same trend as in the previous slide. The decrease in elastic strain at the core corresponds to an increase in plastic strain and transformation plastic strain in that area. The increase in total strain leads to an increase near the surface of the elastic strain distribution. The slide shows the various strain at 52.5 seconds. The decrease in elastic strain at the core corresponds to an increase in expansion strain and the decrease in transformation plastic strain due to multi-stick transformation in that area. The increase in total strain is small. The slide shows the distribution in the final cooling state. During this period, the expansion strain and total strain decrease, and the distribution shape of the expansion strain becomes horizontal. This slightly changes the shape of the elastic strain distribution. The change in the actual stress obtained from the simulation is shown again. On the right side of the slide, the stress distribution qualitatively drawn by Buller and Shire is again shown for comparison. The ratio of the vertical axis has been adjusted for comparison. Except for the presence of state D and the surface side shape of state C, the trend of both distributions are consistent. I'd like to summarize my talk. This paper clarified the difference between the estimated stresses-based approach and the simulated strains-based approach. The former only qualitatively estimate stress changes because thermal and transformation stresses are not specifically available. The latter, on the other hand, logically explain the mechanism of residual stress generation based on individual simulated strains. The latter approach provides a deeper understanding of the cause of problems and facilitate their remediation. Thank you for your kind attention.